Good day, my good scholars. Today we're going to be talking about electron configuration and how it relates to electromagnetic radiation. So, we've been studying electron configuration. We've been looking at 2 to 3 ways in which the electrons can be illustrated in an atom. The first way we looked at was something called Bohr's model, where you had the nucleus in the center, and then you have these rings known as shells, or better yet, energy levels surrounding the nucleus, and where the electrons are placed on each energy level or shell. Then we did orbital notation. Orbital, orbital notation gets a little more details. It identifies the energy level, but it also identified the sub levels or the sub shells. And in each sub level, there's orbital lines that can contain up to 2 electrons that can have opposite spins. We use these up and down arrows to illustrate electrons that spin in the opposite direction. The other type of configuration we study is electron configuration, where you replace the arrows with superscript numbers to indicate the number of electrons. So, again, these two configurations are more detailed. They tell energy levels and sub levels or orbitals. Okay? Whereas the Bohr's model just get directly into energy levels only. So we are going to focus on a Bohr's model today to help our understanding of electromagnetic radiation. So let's look at the definition of electromagnetic radiation. It's the flow of energy at the universal speed of light through free space or through a material medium in the form of electric or magnetic fields, electric and magnetic fields that make up electromagnetic waves such as radio waves, visible light, and gamma rays. So here are 2 illustrations. Here's one, the electric field that has a positive and negative, and the field contains a force that attracts each other. The same for magnetic field. There's a north pole and a south pole, but there's an attraction in this field. So this is where um, that free space for materials to sorry, it's that free space or the material medium in which the electron, I mean, electric and magnetic field exist. Okay, so next up, now when I said we were going to focus on Bohr's model to examine the arrangement of electrons in an atom, we have two particular models. We have two particular states that the Bohr model is going to help us understand. First, there's the ground state, which is the lowest energy state of an atom. Here, this example, this Bohr model is of the element lithium, atomic number 3. Lithium is in the second period of the periodic table. Therefore, it has 2 energy levels. And it's in group 1 of the periodic table. Therefore, it has 1 valence electron. So we know on the first energy level gets 2 electrons. And because lithium atomic number is 3, there's one more electron in place, and that electron goes on the second energy level. And notice it's only one, so this is known as the valence electron. Okay? The electron we're going to find out has a lot of important characteristics to an atom. Then there's something called the excited state. This is the state in which an atom has the higher potential energy. So here we are at ground state, right? This is the regular Bohr's model of lithium at ground state. But when we take lithium and supply it with some heat energy, some type of energy, heat or even light, we can cause the valence electron in an atom to get what we call excited. And when it gets excited, I'm going to add a third energy level to this second Bohr's model over here. When it gets excited, this valence electron does something called it gets excited and jumps to the next energy level. That's the excited state. But just like you, when you get excited and you jump up in the air, do you stay in the air? No. That electron returns back to its ground state, the original state, the state that it really wants to be in. But on its way back, it emits, there's some emission, and it emits electromagnetic radiation, one of the forms of it. Okay. So just like when we did the flame test in the class with lithium, here, this was the emission, this pink or reddish color flame we witnessed in class or observed in class was the electromagnetic radiation that was being emitted from the when the electron was returning out of a excited state back to ground state. So over here, this is called absorption. I forgot to mention that. When you add energy, this heat or light to an atom causes it to get excited and jump to the next energy level, but on its way back, it emits out energy, the same type of energy or similar energy that was put into it. And it comes out as electromagnetic radiation. All right. So, electromagnetic radiation has two variables in which we can measure and it travels in. Well, it's a wave. So, all radiation is a wave. It travels as a wave. And one thing we measure about waves is something called wavelength. We use the symbol for wavelength, this Greek letter called lambda. And a units that wavelength is measured in is nanometers or meters. So over here in this diagram, at the top of the wave, this is known as the crest. At the bottom of a wave, that is known as the trough. So if you measure from one crest to the next crest, this is known as wavelength. So wavelengths could be large or they could be small. Another variable that measure waves is known as frequency. Frequency is the number of waves over a time period of a second. So for instance, let's say I'm going to draw a line here. Let's say this line that I drew is 1 second. So we could determine the frequency of this top illustration. There's 1, 2, 3. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 waves in that second. So we would call this 9 waves per second. Okay, that's a frequency. But we do not record our units like this. Frequency units is measured in something called hertz. Hertz is symbolized by Hz. It means the number of waves per second. And a symbol that we use for frequency is a funny looking Greek letter, looks like a V, nu. Okay, so those are the symbols, and this is the unit. So again, frequency is the number of waves per second. If we look at the bottom diagram here, we have 1, 2 waves. So this one would be 2 waves per second. So we could rewrite these as 2 hertz or non-hertz. Okay, so that's those are the two variables we measure electromagnetic radiation. Next up is the spectrum of electromagnetic radiation. If you notice over here, this side of the spectrum, we have something called radio waves. You guys are very familiar with radio waves. It's all around us. You hear it. That's the wave that sound's traveling. You're also familiar with microwave because you cook with it. Then there's infrared rays. Infrared rays are like nighttime. What are those goggles? Night goggles, where they want to see in the dark. They use body heat that reflects infrared can pick up on heat, body heat. And then there's a very important region of the spectrum known as the visible region. This is so important because this is the only region our human eye can see. It can see the color red, orange. It can also see the color yellow, green, blue, and purple. So the visible region is so important for the human eye. Ultraviolet, you're also pretty familiar with that term. That comes from the sun. Those are the harmful rays that penetrate our skin and give some people skin cancer. Then there's x-rays. Yes, the same x-rays that when you go to a hospital or a doctor's office to take pictures of your bone. Then there's gamma rays. This is really powerful, high energy waves. The reason why gamma rays are so high energy is because of their frequency. Notice the frequency of gamma rays is 10 to the 20th. That means a number one with 20 zeros behind it. So we could kind of illustrate frequency like this is 1 second, and it have all these little squibbly lines. That would be a frequency, um, a high frequency. The wavelength of this high frequency is small. If you notice, the wavelength up here is 10 to the negative 12. So that means the distance between the two waves is really small. So that would be a decimal point with 11 zeros and a 1. I didn't really draw 11 zeros, but you get the idea. The wavelength is small, but the frequency is high. So if there's high frequency, the wavelength is small. But if we come back to this side of the spectrum where radio waves are, if you notice here, the wavelength is like 1 meter. It's the size of a human, or it could be even larger. So on this side of the spectrum, the wavelengths are real big. But the frequency is, notice, relatively low, 10 to the 8th. So that means in 1 second, you know, the frequency is not as high as in the gamma region. So down here in radio waves, that means wavelengths are high, then frequency is low. And this all makes sense because it deals with the speed of light. All these rays inside the spectrum all travel at 3 times 10 to the 8th meter. You ever hear as fast as speed of light? Well, that's where that term comes from. So let's look at some calculations or some equation. So speed of light is symbolized by the letter c, lowercase c, and the value of it is 3 times 10 to the 8th meters per second. Okay, that's pretty fast. That's a 3 with 8 zeros behind it. So um, it's really fast. But we have a formula, an equation for the speed of light. The equation is c equals lambda which is wavelength, times frequency. Okay? So when you multiply those two variables, they always come out to be the speed of light. Speed of light is a constant. This number will never change. But we can have different values for wavelength and different values for frequency that when you multiply them, you must get the speed of light. So this is what we call a indirect relationship. If one is high, then the other one is low. Okay? And it makes sense. Let's just take a brief look at the units. Wavelength can be measured in meters. Frequency is measured in the number of waves per second. When you multiply the two, you get meters per second, which is the same units as the wavelength. The same units as speed of light. So that's how that comes about. There is another equation that we have to know for electromagnetic radiation, and that's photon energy equation. The symbol for photon energy is E. It is measured in the units of joule. Energy can be measured in joules or calories, but we're going to just focus on joules. So photon energy equation is E equals H. H is known as Planck's constant. This is another number that does not change. It will always be 6.626 times 10 to the negative 34 joules second. Okay, so energy equals Planck's constant times that's supposed to be frequency. When you multiply the two, because let's look at the units. Here's Planck's constant units. When you multiply with units from frequency, which is hertz, which is number of waves over seconds, the seconds will cancel out and you will multiply the number, and only unit you have is joules, which is energy units. So don't worry about it quite yet. Don't be intimidated. These are two very easy equations. Either you're multiplying or, no, not or, you're multiplying for both. So there's no need to be afraid, especially for this one, because Planck's constant is given to you. All right. So let's proceed on and learn how to determine the energy and measure some wavelength and frequency of different colors on the electromagnetic spectrum.